interface between Geant4 and Opticks. We developed a prototype example to show, to demonstrate the use of GE for optics. Then I have some preliminary numbers on performance and then summary and plans. So in principle, a liquid argon TPC is just a volume of liquid argon. We have an electric field between a cathode plane and a readout plane, which can be either made of stereo wires or pixels. And when the particles interact, they produce two signals. One will be the ionization electrons, and the other, which in the presence of an electric field will drift to the cathode plane, to the wire plane and be registered, and scintillation photons, which isotropically will be emitted from the point where they are produced. On the lower right, I just show a typical ionizations displays of two different events, and we can see there's a lot of information and a lot of detail that you can get out of this kind of technology. On the next slide, I don't want to get you into too many details about the physics. What are the main points are that liquid argon is a very good scintillator. You produce something in the order of 100,000 photons per centimeter. We also, as I already said, we have to deal with two signals, namely the electrons and the photons, when we simulate it. And the photons in liquid argon are in the vacuum ultraviolet. That means to be detected, you need a wavelength shifting process implemented in your simulation. So let's go to the next one. So what is the motivation for using this? If you are brave enough to use Geant4 standalone to simulate the photon propagation on the CPU, it takes in the order of hours to simulate one event for a typical liquid argon TPC. So the current liquid argon TPC experiments use lookup tables or parameterizations for the photon response, but that is only an approximation. The information is not complete, and the lookup tables will grow with the size of your detector to the point where your job can't run on a typical grid node because your memory requirements become too big. Also, you still need a full simulation to create the tables in the first place. What Simon shows is that with optics, you can speed up the photon simulation to the level where it is comparable to the rest of the simulation or even faster. And what this will allow you to do a full optical simulation event by event, and you can actually start investigating different ideas, like, for example, improving energy resolution by correlating light and the ionization problem. And one thing I should say is this is not just liquid argon TPCs, but it will benefit any experiment where you have to deal with lots of optical photons. So Opticks was developed by Simon Blythe. It was developed for the Chinese Cherenkov neutrino experiments, and I have put two references here to the Simon's talk at the Geant4 R&D forum and some of his presentations. But what I wanted to say is that they ran into the same problem, that doing the full simulation on Geant4, they found out that about 99% of the CPU time and memory is used by the propagation and generation of optical photons. And so, and on the other hand, the problem of photon propagation and generation is actually a very good example for effectively moving to GPUs, because you're only dealing with one particle. The physics which is involved is very limited. You only produce it by either Cherenkov or scintillation, and you only have to deal with typical processes like reflection, absorption, Rayleigh scattering. So the list that you have to implement is very limited. So if you do it on optics, which uses NVIDIA CUDA and optics, you basically bind yourself to a very specific hardware and software. And while this comes with, while it locks you in, it also comes with the advantage of high efficiency. So you have high efficient C++ libraries in CUDA and the specific libraries in optics to calculate the intersections. And one additional advantage of modern GPUs by NVIDIA is that now you have the ray trace accelerated by hardware. So you get another gain by offloading the ray tracing to specific RT cores. So what is optics? What is G4 optics? It translates the G4 optical physics to CUDA optics. And the way it is done is basically you split the production processes like Cherenkov and scintillation in two parts. One which runs on the CPU and collects all the information that you need to generate the photons. And then you ship this information to the GPU, which then generates the photons, transports them, and what you get back after this is done are the hits, basically the photons which hit a photon detector. So overall, you spend relatively, you try to copy very little data between the CPU and the GPU. You copy the information, the so-called GAN steps, to the GPU, and then you copy the hits back. And so originally, that's what I crossed out here. This was done by modifying the Cherenkov and scintillation process themselves. When you, but we found that it's possible to just use the available Geant4 user API to access this information. So you really don't have to worry about changing Geant4 code itself. So if you look at the list of processes, there's one that sticks out. The wavelength shifting still needs to be implemented, but it's very similar to the scintillator re-emission process. So it will be very easy to do that. So what's the G4 optics hybrid flow? On the left, we saw Geant4, where everything is done on the GPU. In the hybrid flow, as I said, there's two things. First, we have to translate the geometry into a geometry used by optics. It's a discrete geometry which currently supports 10 shapes. Then from the scintillation Cherenkov process, you collect the information that you need to generate the optical photons. This you copy to the GPU, and then on the GPU, you generate the photons, trace them, and in the end, you copy the hits on the photodetectors back and write it out. There's a little bit one has to know is that currently, the scintillation process on GPU is not exactly the same as in Geant4, so there's some work to be done. We still have to implement the wavelength shifting process, and currently G4 optics is invoked at the end of the event. So you don't have true concurrency. You run Geant4 and then G4 optics. So one of the things we want to achieve is to make that truly concurrent by using the G4 tasking framework, which will be available with the next Geant4 release. So what is G4 Opticks Test? It's an application to demonstrate the use of G4 Optics hybrid flow. We plan to make this a Geant4 advanced example. The code is available in GitHub at the following link. The features are: we do the harvesting of scintillation and Cherenkov-Gens steps in the sensitive detectors or user stepping action. We then use optics to generate and propagate the optical photons and return the photon hits. We use GDML to describe the detector geometry and detector configuration. And we extended GDML to basically assign sensitive detectors to logical volumes to do specific physics parameters. For example, we need to apply step limit to the liquid argon active volume to match the Geant4 steps to the pitch of the TPC readout. We also assign visualization properties and homogeneous electric fields. We make use of formulas, variable loops, and predefined NIST materials to achieve a compact human-readable GDML file. For physics, we make use of this physics list factory, which allows us to really specifically configure the physics by just combining, in this case, the FTFP reference physics list in Geant4 with optical constructors, the step limit constructor, and the neutron limit, and we use root IO to provide persistency. So the next slide just shows the G4 Optics Test workflow. As I said, the detector configuration geometry is given by a GDML file, so no recompilation required if you change any of this. The physics configuration and the control of the running is done with a Geant4 macro, and then at each step in the process hits part of the sensitive detector, we collect the electrons and put that into a Geant4 hit collection, the so-called LAr TPC hits, and we collect the information to generate the optical photons in the Gen steps, and the Gen steps are different for Cherenkov and scintillation. So then at the end of the event, we directly write out the LAR TPC hits, while the Gen steps are copied to G4 optics, where the photons then are generated and propagated, and whatever hits the photodetector will be copied back to the photon hits, which are then written out into the root file. So standard high-energy physics workflow. So what is the performance? So for the performance tests, on the top, on the left, you can see the hardware we were using. On the top, on the right, you see the geometry we were using. Basically, it's a 1 cube of liquid argon, 1 cubic meter cube of liquid argon, and we have 5 photodetectors attached to one side. So very similar to the picture we saw at the beginning. And on right on the bottom, you will see the histogram of the position of photon hits that we get out of the file. So now on the bottom left, I show the first benchmarking results. And what we have here are basically three configurations that we run the simulation with. In green, the difference between the green and the red curves are that we use a different memory configuration. We keep track of the which photons are produced by each GAN step by keeping a random number seed buffer, and basically the size of the random number seed buffer will determine how many photons we can produce. And we can see if we create a bigger buffer, we have to pay a price in CPU performance. So that's the difference between green and red. And the difference between the red and the blue curve is we enable the hardware acceleration on the NVIDIA GPU card, which gives us another factor of 2. The importance and the x-axis, what it does is what it says. It tells us how many photons are produced per MeV. What is the photon yield? And 50,000 is where we want to be for liquid argon TPC. That's a very typical number. On the left, on the y-axis, we see the seconds per event, and we can see that compared to the hours per event, which we had with Geant4 alone simulation, we are now down to about a second per event. So this is very, very encouraging. The picture on the bottom in the middle just shows the usage of the GPU, and we can see that we make pretty good use of the GPUs in this example. So the time goes left in this picture. We can see the startup, and then we basically have a flat, full-out use of the GPU. So this is very encouraging. Let me go to my next slide. So what are the summary? So we made optics work with the latest version of Geant4. We have a prototype application, G4 Opticks Test, which is available, and we plan to make it an advanced Geant4 example. We have various geometries that are available in form of GDML, and the preliminary benchmarking looks very promising. The plans are to implement the current Geant4 scintillation process one-to-one on the GPU, implement the wavelength shifting process on GPU, and to develop true concurrency by making use of the Geant4 tasking framework, which will be available. And there we basically would collect on Gen steps on the fly until a specific chunk size is reached, and then we would ship that onto the GPU while Geant4 continues doing the simulation of all the other particles. And finally, I want to say special thanks to Simon. He really, for providing the code and answering our sometimes stupid questions. And that's about it.
Okay, thank you. Hans, let's see. I don't see any hands raised. And okay, any questions?
I don't see particular questions written, nor from hands raised.
Okay.
There are 2 hands raised now.
Ah, okay, good. Ben?
Yeah, just another comment on the offloading. So I'll take a look at the examples. It's great that we have this, because I'm just seeing your comments on this slide about gen steps being chunked and collected in situ, and then once you reach a chunk size, it's offloaded to the GPU. It sounds like this would be a very interesting thing to see from the Adepts and Celeritas point of view, because I know something I think Andre mentioned is how to offload to the GPU efficiently. So this could be an interesting thing to look at from our perspective, I think.
Yeah, so basically what you get will be, if you look at these curves, the difference between these curves is basically this real time and CPU time. And basically, if you make the offloading to GPUs more efficient, you will basically move the lower curve, the upper curve down to the lower curve. And this will be more important the more complex and the bigger the LAR TPC will be. Yeah,
so that's the sort of green, so the earlier offloads or more efficient offloads is the blue curve versus the green?
No, if you have to compare 2 graphs of the same color. And
gotcha.
The upper one is the real time, while the lower one is the CPU time. So, and basically what it means, the CPU is waiting for the GPU. And the more photons you produce, the longer you have to wait. So if you can upload more efficient to the GPU, you basically bring down the upper green curve to the lower green curve. And what you expect is, this is a very small liquid argon TPC, but that the discrepancy between these curves will just increase as you go to bigger liquid argon TPC and more complicated geometries.
Yeah, that's great. Thanks.
Okay, John, please.
Thanks. I didn't quite understand the differences between the different color curves. So if you would mind repeating it, it would be rather helpful.
Okay, so for each of these curves, the same color means real time compared to CPU time. So to make that, then we have different memory configuration. Basically, what we do is we keep track of the relationship between the gen step and the photons that we detect by having a random number seed buffer. So basically, what it means is it gives you the number of gen steps that you can use and ship to the GPU. The upper one uses something like 100 million random number seed buffers. The red one uses 10 million. So that will limit the total number of photons you basically can propagate. But in this case, we see that the red one is good enough for that case. And then we see that having this additional memory overhead, you pay a price in time. If we now go from the red curve to the blue curve, what happens there is we switched on the NVIDIA hardware acceleration, RTX, and that gives us another factor of 2 in speed. Does it answer your question?
Partially. The information is the extra information that you're keeping. I would expect would be more trajectory rather than random number information. And is it shipped to the GPU or is it kept on the CPU?
I think it's kept on the CPU because but I'm not sure. I have to look at that myself.
Thank you.
Because if you look at the plot in the middle, you don't see movement in memory on the GPU. So I think it is kept on the GPU.
Okay. Well, thanks a lot, Hans. It appears we are ready. Let's see. And that is the end of our presentation.